All right. I enjoyed looking over everybody's comments about stress and strain. I'm not going to test you on that just because we don't have enough time to cover it in enough detail. Today is going to be all about solving problems. But let me just give you some vocabulary in case like this comes up on the MCAT. So stress is not the same thing as force. Stress is a force applied to an area. So if I take this water, or whatever, it's water, okay.
What are you talking about?
This water, okay. So the water has a certain weight. When I place it on the table, that weight is distributed over the area of contact. Now, this actually has a ring, so it's not a very big area. The stress is the force divided by the area it's on. And so you can have very different stresses with the same force. For instance, a very classic physics problem is here I am, a grown man who weighs a lot more than he should, and that weight is distributed over the area of my shoes, which is reasonably large. So the stress I'm applying to the floor is fairly small. But if we were to take Sarah, the opposite of me, and she were wearing stiletto heels, her smaller, much smaller weight would be placed, if she leans back in that heel on a very small area, and that would make a very large stress. And so Sarah could easily dent the floor because she'd be applying more stress than the ultimate strength of the flooring material. So stress is the force divided by the area, which means its units are, what are the units of force? Newtons divided by what are the units of area? Area is distance times distance, so it's meters squared. So stress is in newtons per meter squared. Now, there's more than one type of stress, and there seems to be some confusion in people's comments about that. So here's the three types of stress. Stress number one, I take my hand, I press into the table. I'm trying to compress the material, so we call that a compressive stress. So when the force is into the surface, it's a compressive stress. Now for the other two, I have to glue my hand to the table. So now my hand is glued to the table and I pull up. That's a tensile stress because I'm putting the table in tension. So trying to stretch it is a tensile stress. And the last one, my hand's on the table, instead of pushing down or up, I try to go sideways with it. We call that, where the force is in the plane of the surface, a shear stress. So we have three different types of stresses, and different things will respond differently to the stresses. Some things will be very strong under compression, but weak under tension. Why? Well, when you try to compress them, you're trying to move the atoms closer together. And they're going to not allow that to happen very well. But if you try to pull them apart, you're trying to separate them, they may not be held together very strongly. And so you can pull it apart fairly easily, but you can't compress it very much. And so you have different ultimate strengths, that is different compressive stress versus tensile stress, and likewise shear stress that will break them. Andy.
So would it be fair to dumb it down and say pushing, pulling, and sliding, or is that not accurate? How are they different if it is?
Pushing, pulling is reasonably accurate. Sliding is, because it has the aspect of motion, instead of just the direction of force, it's a little less clear than the others.
Okay.
By the way, let me point out, in case you haven't come to DJ for tutoring, DJ is here. He is otherwise listening to the lectures that are uploaded to Moodle so that he can help you in working homework, understanding concepts, whatever you need. And he's available Sunday nights 6 to 8 and Thursday nights 7 to 9. One last thing on this stress strain. Now, when I was in graduate school, how many people here are planning on going to a professional school or a graduate school? That's a lot. There's a lot of stress there. What did I just define stress as? Okay, those are types. A force over an area was the definition of stress. You went with the types of stress, which is, fair enough. But okay, that was important. So stress is a force over an area. So when we talk about mental stress, it really does make sense. It's kind of like a force on your brain, right? Your brain is being, I would say, compressed. And so strain is how an object is deformed due to the stress. Somebody in the perusal was questioning, so does that mean anytime I press on an object it gets deformed? Yes. Yes. If I take this, I'm not even squeezing hard. It's deformed. Very, very small, unmeasurable amount, but it is. If I squeeze harder, it's probably not going to be strong enough to deform this in any way. I made the mistake once of squeezing a mug and it shattered in my hand. Casino. Okay. So strain is a measurement of the deformation that occurs due to the stress. And so when you are in graduate school and under a lot of strain, there may be some, or under a lot of stress, there may be some strain that shows. And of course, oftentimes we use derisive terms, but it's a real thing and it's something that needs to be cared for. I had 2 classmates who showed significant signs of strain. They happened to be dating each other, which I found an odd coincidence. We came to a test and one student had a bunch of just big red things on her cheek. And I'm like, "Whoa, what happened?" Well, I was studying and she was gouging her face with her fingernails while she was studying. That's clearly a strain, a response to the stress. And another one had no more eyelashes. We were studying going like this until there were none. That kind of obsessive behavior is a clear sign, right? It's a strain, and it means that you are under too much stress. And I'll tell you what, I sincerely do not believe that Randy's solution is the right one. I sincerely believe that we have the biggest blessing in the world that God gave us the Sabbath day. A day to relax. A day when I was in graduate school, I would have felt tremendous guilt if I were to be studying on that day. It was a day when I allowed that stress to dissipate. I think that was helpful to me not having these strains that my classmates were having. Moving on, I'm sorry, Randy did make me laugh. And I trust nobody else saw Randy's answer, except for Max.
Nothing to do with what you were saying, but still.
Okay, so in class on Wednesday, we had our first what we call statics problems. I'd be willing to bet that 2 of our students wish I would have done more of that since they just had a test on that. Today, I'm going to be doing some statics problems and some dynamics problems. So nothing but problems today.
Yes.
So first, our review of Newton's 3 laws, because that's how we solve these problems. So the first law, the sum of the forces on an object, if the sum of the forces is 0, then the object will not accelerate. The second law tells us what the acceleration will be if the sum of the forces is not 0. And notice, if the sum of the forces is 0, the second law gives you the first law. And so the second law is the one that we are going to use over and over and over again. And then the third law says if a semi puts a force on a Prius, the Prius puts exactly the same force on the semi. In the opposite direction. That's what the minus sign is for. So those are our key equations for solving problems. And then steps. When you're solving these problems, if you just follow a set of steps carefully, even if you had no idea what was going on, you should be able to solve them. Which is kind of the goal, because you see a new problem that you've never encountered before, which is ideally what every question on the test is. to solve it, you have to think what's going on and have a method to go through and do it. So, first thing is always draw a diagram, identify which object you're interested in. That wasn't part of our kinematic stuff, right? We had the object, it was pretty clear. Now it's not always so clear. Like you had in the textbook, the thing with the woman pushing the child in the wagon. Is your object the child? Is it the wagon? Is it the child and the wagon? You have some choices to make. Then you draw a free body diagram for your object. All you care about is the object. And you only show external forces. Once again, on Perusal, there was a lot of discussion. Do you guys ever go back and see my answers to your questions? Nope. Well, I do try to be responsive, yes.
I see them because it sends like an email.
Oh, it does, it updates you. Cool.
Yeah, so I can see your response in the email, but I don't like go back in and look through it because it's not like.
So it's at least somewhat useful. Like,
yeah.
I explained about, back when I was a kid, they were putting bleach out there for the burnouts. Now apparently they use water. So you don't put internal forces, only external forces. What's the difference? An internal force is between two objects within the system. So if in the example I used, I choose my system is the wagon and the child, the force that the child is putting on the wagon is internal, because both the wagon and the child are inside my system. I don't include that because Newton's third law says for every force there's an equal and opposite force. So the force the child puts on the wagon is equal in magnitude in opposite direction to the force that the wagon puts on the child. So if I add those two forces together, what do I get? 0. So why would you put those in? You can have a very large number of forces if you included them, but if they all add to 0, it's not helping you. So we only do external forces, forces that are acting on my system from something outside of the system. Then, notice I have a star here. Oh, put your coordinate axes, that's always important. Break forces into components. If you have only 3 vectors, it'll probably be quicker to just use law of sines, law of cosines. If you have more than 3 vectors, you've got to do that. So it never hurts to do this. In fact, I used to never use the law of sines or cosines, but then I was looking at student solution, I was like, wow, that took a lot less work than the way I did it. So that's why I show you both ways. Then apply Newton's second law independently in each of your component directions and solve. And finally, check to make sure the answer makes sense. So that's a set of steps for solving a problem. So if you identify, hey, this problem is going to be one that I solve using Newton's second law, then you jump straight to doing this method. Now, not all problems are solved that way. Part of the physics is identifying how am I going to solve it, but that's, once you've identified it, then you do that. So this problem that I was looking at in class, and then I had a different problem that was actually identical in work. I'll work this out, and then I'm going to give you the following one for you to work out at your tables. So here I have a gentleman on a tightrope, and I'm asked what the tension in the rope is. So the first step, draw a figure. It's there. Second step, what was the second step? Well, actually, it was identify my object. And so, what is my object? Okay, I have 2 different answers.
Says the system of interest is the point of the wire.
What?
It just says system of interest here is the point in the wire.
Oh, okay, so it tells us the answer to the problem. Trust me, that's never going to happen on a test.
Oh, come on.
It's part of the reasoning process that we're trying to develop in students. It's identifying what the object is. I should have deleted that text because, if you can read it, it takes away you having to go through the process of identifying. So we have that little piece of rope, and then we say what forces are acting on that rope from external to that piece. Now, it's not the entire rope. It's that little piece of rope. So you have the rope going off to the left, the rope going off to the right, and the person's foot pressing on it. Because our rope is so tiny, we're not considering the weight of that little piece. And after all, in physics, we make the approximation that the rope has no mass. Now, I've been kind of mocking that this year, haven't I? The approximation of no air resistance, approximation of no mass in our rope, approximation that the rope doesn't stretch. Do these approximations make a difference? Yes, they do. But at the same time, if you're in the right situation, they don't. For instance, if I drop this pin, gotta be careful, it's $100 pin. Yes, I know. Microsoft is trying to be like Apple. We're the only one that makes it. We can charge whatever we want. Okay, so if I drop this pin for any reasonable distance, the drag force is going to be very small compared to the force of gravity. So the net force will be indistinguishable from just the force of gravity. So ignoring air resistance won't matter. But of course, if I dropped it from the top of the Sears Tower, by the time it gets down near the ground, it probably will matter. For those who care about this kind of thing, you probably heard that if you tossed a penny off the top of the Empire State Building and hit somebody on the head, what would happen? But Mythbusters, who made a job of actually testing these things against real life, they determined that the terminal velocity for a penny is actually reasonably slow. They modified a staple gun to shoot pennies. And they shot them, and they found out quickly that the speed they were shooting at them was higher than the terminal velocity. They would slow down after they shot them. And if you stand far enough away and shoot it at the person, it doesn't really, it'll leave a welt, but it's not really dangerous. They also did one where they threw cards. And that's a little more dangerous. Card got stuck in his chest. Not very far, but it broke the skin and stuck there, which is funny. I'm sorry. Back to the topic. We have drawn the picture. We have done the free body diagram. What do we do next?
Determine which equation goes with it.
We need to get our coordinate directions. And then somebody said identify the equation that goes with it. If you're doing a problem that is a force problem, that equation is Newton's second law. Now, you might have some other equations, like if you have a spring, what's the equation for the force of the spring? If you have friction, what's the equation for force of friction? But Newton's second law is your fundamental equation. So then I have the one with an asterisk.
Components.
Break the force into components unless you have only 3 vectors. Here I have only 3 vectors, so I could do it without components using trigonometry. That's what I did in class Wednesday. So today I'm going to do it with components. And so now I have to say, okay, my x direction and my y direction, the force tension left, and force tension left then is going to be this one here. So it says TL. Has a magnitude of tension for the force. Remember, tension is the magnitude of the force that's being distributed by a rope. But then if I break it into components, because of this 5 degrees, my components are upward like that and to the left like that. So based on that 5 degrees, is the horizontal, the x component, the adjacent side or the opposite side? Adjacent. Which trig function goes with adjacent? And is it positive or negative in the x direction? Negative. Now for the y direction, it's going up, so it's positive for the y direction. So I have here plus tension sine of 5 degrees because it's the opposite side. Now I have to do that for the force of tension on the right side as well. I didn't go through all the explanation again because the only difference is it's going to the right now instead of to the left. In this problem, the angle was the same, so I didn't have to really repeat anything.
So that's two forces. What's the third force? There's three forces in my free body diagram. And by the way, I usually make my free body diagram just like this. I don't draw it separate. That's up to you how you want to do it. Just make sure you have all the forces acting on the object of interest and no extra forces. So what direction is it? Down, which in terms of x and y is minus y. And then it tells us the magnitude is 840 newtons. So now I have two problems. One's the x direction problem, one's the y direction problem. The x direction problem, I could have put tension left and tension right like the book did. And if I did that, the left problem would have been just add everything in that column. Sum of the forces in x is equal to max. Because it's staying constant at no motion, acceleration is 0. And so I add that column, I have minus tension left cosine 5 degrees plus tension right cosine 5 degrees equals 0. That then demands tension left must equal tension right. Since they both have 5 degrees, I just cancel the 5 degrees. And I have... So that's what I would have had if I would have used tension left and right. I didn't use left and right because I already knew that. But you know what? You didn't know that necessarily. And in fact, in the next problem, the one that you're going to do, that's not true. So you do have to have tension left and tension right for your problem. Now going to the y direction, sum of the forces in the y direction equals mass times acceleration in the y direction. What's its acceleration in the y direction? That's what it would be if it was in free fall. It's stationary, right? And so how much is this velocity changing if it's stationary? 0. So the acceleration is 0 again. And so add that column, tension sine 5 degrees plus tension sine 5 degrees. Notice I dropped the left and right because I just showed that left and right were the same. Minus 840 newtons equals 0. Okay, I can move over, don't have to. Well, that's pretty simple. 2 tension times sine of 5 degrees. I'm sorry, my 5 degrees looks horrible. Equals 840 newtons. Divide both sides by 2 sine of 5 degrees. And you get tension equals 420 divided by sine of 5 degrees, whatever that is. That's how you solve a statics problem, a problem with constant motion, no acceleration. Statics actually means stationary. But if it's constant motion, it's still going to be the same solution method. Any questions about that solution? All right then, your turn. A more complex version. You have a traffic light with a mass of 500 newtons. You have the angles are 30 degrees on one side and 45 degrees on the other. And you are asked to find what tension 1 and tension 2 are. So work with the people at your table. And don't ignore them and do your solution separately after the top.
Wait, I have a question.
Yeah.
So I did it this way first before you started.
Yes, that's right. That's right. That's how I get class.
Like, would that be fine if I
Yes. Right. That's right. The reason I did it different today was so you see it done both ways.
And G1 is a very degree of fire. Sorry.
And that's
Yeah. What's your status? Let's see. Oh, teach me statistician. So first.
But it has nothing to do with aesthetics.
Okay, 1 point. Because what we're looking for is initially
Okay.
But this. And that. So what we have here is
See, most people have Freebody Diagram, basically.
Don't touch me. It was really
Where's your notes?
Oh, that was what you said. I heard.
I'm just repeating that too, because I'm forgetting.
Okay, we're all the same page.
It was this one. No. No.
This is
But it has something to do with physical needs as well, because this one didn't have degrees.
Oh, wait, mine's not.
Okay, so how is this wrong? I get what you're saying.
So you can't assume that.
It's gonna be like.
Which one's
So we can just.
but some of them.
Oh, the five. Some of this five.
The sum of the vertical is fine.
To get the. So that would be the math of traffic.
This is where I stopped.
We have to find the master traffic.
You did.
So it'd be, because that's gonna be your factor.
I get that. Then the Y.
Find it together, how much the traffic is.
Right, so
So you're gonna do.
Oh.
G divided by 9.
one of them's 30 degrees, one of them's 45.
Right, T2 was 45.
No, because it's
T1 is 30.
Okay. A and B.
Okay, now.
Okay, so now that should be correct.
It's closer to the right side of these T2. And think of it like
Okay,
this.
that
So you have-
equals 51.82 equals.
But now
nine.
we're
Then define the tension of the one, its mass times acceleration plus the vertical. So for T1 it's 30, sine 30 and cosine.
Do you not have contacts?
Then it's supposed to be for angle.
Yeah, it's 45 degrees to the right side. To make it so you have to think it through. So it's not just the same as the carbon did.
Cracked the first day.
Yeah. No, I think it's no why sine 40 divided by this is the force perpendicular, which is it's 30 plus 60. Here 2.
That's adding, so this is essentially the.
Actually, it didn't say that. Remember,
Actually, will we do 30 plus 25?
Then it wouldn't be.
It wouldn't be yeah.
I'm gonna do the next problem. I'm gonna do. Okay, so yeah, that's the line version. So we'll get to that thought process after finish.
Still be a triangle.
And if you chose some other orientation.
Then what do we do with the mass of the track? Just like doesn't that come into play too?
Sorry, please.
That was.
Yes, sir.
I don't know.
Diagrams. You have your direction for that?
Second amendment. Got you. Hey, don't worry about your It's kind of a talk. It's talking about the same.
Now, you have two ways to do it. You can, because they're all two values here.
So then we still make
That's right, that's.
So we do 30 plus 45.
If you draw your triangle right.
So then it'd be.
Divided by the force perpendicular, which is 500. But is that the function of tension 1 or function 2? Like if you're using what we had in our homework, I think I similar thing on one of them.
So zero.
We have like tension 1.
Oh, I did for
So like I got this.
Well, actually,
So it's completely different.
no, you can't even. Well, I guess you can make it.
So this
No, the other.
would we do it the sign of.
I see. Here. What? Sorry, sir. Need that.
So, this is 30 meters.
So then verify each of these and then we determine what your speed.
And then you go forward, so this is 90, that makes this.
And this is what you would put in. So if you're trying to get 1, which would be
But I see it.
this one.
You
This
better
would be your 75. And then this
You
would
can't
be.
even do that because it's cosine is sine. Oh, you can do this. This one. You can't. You can. Come here.
Okay, so then.
You can.
47. So
You
it's like
can.
over 2. And then.
If I subtract this, and just the 2 since this is already negative, you just cancel since it's already negative. So now the T1s cancel. Oh, there's sine and cosine trackers.
That's the.
The only thing that I don't, I can use 25 and 30, I don't. get heavy loading 30 and 45.
The reason is because lower is in comparison to the light. It's not, our other angles have something on top of the lighter side and not.
But can you have it? What? Here go. You can't go my favorite elements.
I'll be there.
Is your cat loose?
No, I'm gonna grab Paul's short now.
Okay, so those are parallel lines.
No, he doesn't. Exactly, you need one length. But that's just, give me both angles. What I gotta do? You ain't got two more. I need a yes.
I can't draw you guys.
And so if a line crosses two parallel lines, the angle it makes between them is the same. So, but you have to go on opposite sides. So since this is 30, then this must also be 30.
I think she understands that, she's
Oh,
just
okay.
confused on why.
Yeah, I'm just not good at like visualizing like how you make the two things come together. I just memorize that like they do. And like I get that the 30 and 45 get added together. I'm just not good at like making a triangle on the outside. Like I was known to do the outside angles just because like I can't see it. I can't make it.
I never did those.
Hold on.
Right, I get that. Okay, yeah.
Is this 5
Yeah, that's fine. Okay, it looks like most people have made some reasonable progress.
Wait. Check this out.
Except for Max. Here, look at me.
Look. If you subtract this, right? T1 sine over T1 cosine. Isn't that T1 tangent there?
And also, it's two separate equations. This equals 0, and this equals 0. You don't want to combine them. You want to take this and solve for
How? But they both equal 0.
is equal to T1 cosine 30 cosine 45. And then you put that in here.
Come again? Okay, I got it. Well, like,
You solve one equation for one.
But you don't understand the.
no, they do.
But then you won't get there, yeah.
Okay.
Okay. Either you've solved it or you've run into problems. So now let's look at the solution. And if you had confusions, we can clear them up. And if you didn't, well, it'll just reiterate what you just did. So for this problem here, I have fundamentally the same thing, except for my triangle is different. So I'm going to draw my Freebody diagram, and I have to check again and again and again. Tension 2 at 45 degrees above horizontal. Hopefully that was tension 2, yeah. And tension 1 at 30 degrees above horizontal. And then finally I had force of gravity equals 500 newtons. And as always, you need to define a coordinate system. And for now, x, y being vertical and horizontal is our easiest choice. Other choices you could have made that wouldn't be super hard would have been to make it tilted 45 degrees or to make it tilted at the 30 degrees. Why did I choose those angles? Because then one of my three vectors would not require breaking into components. It's already resolved. Any other choice, and you have to break all three into components, it gets harder. So now that I have that, we have two methods. And I'm going to do both methods quickly. One method is, well, both of them rely on Newton's second law. And so if I do it graphically, I'll have tension 1 plus tension 2 plus force of gravity equals 0. If it equals 0, then I have to be back where I started. So it forms a closed triangle. Now with this triangle, I knew that this angle here was 45 degrees. And I knew that this angle here was 30 degrees. Right, I put in the same angles as I had in my original. But if this angle down below that you can't read is 30, then this is also 30 degrees, which means that I have a total interior angle here of 75 degrees. And this angle here had to be 45 degrees because T2 was at an angle of 45 degrees from horizontal or vertical. And then finally, this one here had to be 60 degrees. So I used geometry to get those angles. And now I can use the law of sines. To save myself one stinking math step, I'm going to put it as T2 over sine of 60 degrees equals T1 over sine of 45 degrees equals FG over sine of 75 degrees. Notice T1 is opposite to 45. T2 is opposite to 60, and FG is opposite to 75. That's how I got which side goes with which angle. And now since I know FG is equal to 500 newtons, then I can just say T1 is equal to 500 newtons over sine 75 degrees times sine of 45 degrees. And T2 is equal to 500 newtons over sine of 75 degrees times sine of 60 degrees. And so there's the solution doing it geometrically. As I said, that's generally going to be easier if and only if you only have a total of 3 things in your Newton's second law. So 2 forces and 1 acceleration, or 3 forces and no acceleration. Otherwise, you're going to have to break it into components. So coming back to my picture and breaking it into components, the force from tension 1, 30 degrees is the angle between X and my force, so that means it's going to be cosine 30 degrees, minus because my X was positive to the right, but tension 1 is going to the left. And then in the Y direction, opposite side is sine, T1 sine of 30 degrees. Go on to 2. Force of tension 2 is equal to tension 2 cosine of 45 degrees plus tension 2 sine of 45 degrees in the Y direction. And then finally, force of gravity, 0 in the X direction and minus 500 newtons in the Y direction. Why did I break these up into components? Why did I draw the Freebody diagram? The answer is the same. What's the whole purpose of our Freebody diagram? Newton's second law, to apply Newton's second law. We broke it up into components so we could apply Newton's second law in each component direction independently. And so on the left-hand side, I'm going to have some of the forces in the X direction is equal to MAX. AX is 0. And so I'm going to have minus T1 cosine of 30 degrees plus T2 sine, cosine of 45 degrees equals 0. Going to the Y direction, I'll have some of the forces in the Y direction equals mass times acceleration in the Y direction, where acceleration in the Y direction is 0. So tension 1 sine of 30 degrees plus tension 2 sine of 45 degrees minus 500 newtons equals 0. So now I have 2 equations, 2 unknowns. As long as you have linear equations, if the number of equations equals the number of known unknowns, you can solve it. And I know 2 of you have been doing this with your calculators, doing row reduction. We're just going to do this the old-fashioned brute force method. Solve this equation for either T1 or T2. Choose. Choose you this day, T1 or T2. Go ahead.
Hey, Terminator 2 is better than Terminator 1.
T2. Okay. So if I want to solve this for T2, the first thing I'm going to do is add T1 cosine 30 degrees to both sides. So I have T2 cosine 45 degrees equals T1 cosine 30 degrees. Divide both sides by cosine of 45 degrees. And I have T2 is equal to T1 times cosine of 30 degrees over cosine of 45 degrees. And of course, you have a calculator. That's a number, right? Now I go to the right-hand side and I substitute that in. So I'll have T1 sine of 30 degrees plus parenthesis T1 cosine of 30 degrees over cosine of 45 degrees, sine 45 degrees. So that thing in parentheses was T2. So now I have T1 in 2 terms on the left. I'm going to add 500 newtons to get it on the right-hand side. So I will have T1 times sine of 30 degrees plus cosine 30 degrees. And to make my writing easier, sine 45 over cosine 45 is tangent. Remember, I added 500 newtons to both sides. And so finally, I get that for T1. And once I pop that in the calculator, I put that in here to get T2. Both were very doable. But if you can use the trig method, it's going to be quicker, right? That is the law of sines. To
Like, to the one that we were.
how I did what?
Like how you form
How I formed.
the triangle in the first example.
Okay, so I have those 3 forces, right? I have the orange one, the magenta one, and the green one. And my Newton's second law says that sum of the force is 0. So if I add those 3 up, it has to come to 0, which means it has to close on itself. And so then I just drew those 3 vectors added together. So I didn't color code them, but you can see T2 is the same direction. Oh, right. So there's T2. That's just the same as that T2. And then here's FG. That's just the same as that FG. And whoops, wrong color. And here is the T1. That's just the same as that T1. So I was rearranging the vectors so I show how they add. Remember, that's why it was on the test, because it's important to be able to do this. Oh, goodness. Well, for my next trick, we'll get together tomorrow. Well, not tomorrow. Tomorrow's Sabbath. Monday. So we had some practice solving Newton's second law problems, and I will do more Newton's second law problems on Monday because we just got to do more and more of them until it gets comfortable.
So Alina and I did it this way. Obviously, that's not right, but we don't understand why. Like you could like T2 divided by sine squared T over divided by sine squared divided by sine squared
No, 75.
Yeah.
No.
Yeah.
Okay.
Like the peanut layer. And we did it like this.
Or you scoop back.
We did
Go scoop back.
we like
Did I make a mistake somehow? No, I didn't make a mistake.
Maybe I didn't. Wait. Actually, there's a Oh, it is right. I just put it into my head.
I'd be worried.
Okay, I was like, okay, so then how does this what? Step? I mean, what? Step?
What do you say?
It's just inverted.
No, it's just like.
Right, so instead of five,
So the T1 and T2 are both in the equation at one time.
I just.
no, just which one's on top and which one's on bottom.
Did you
That's
know?
the same equation. It's just I didn't have to multiply it across.
Did you know? Hey, bro, I'm just. We about to go to Columbia for that.
So I mean, you'll see the law sign here in both ways.
It's at this point that everybody realizes there's